All right, we're going to get started. Hi, everyone. My name is Joe Ugalde, and I am the Marketing Business Analyst at TE Wire and Cable. On behalf of both the teams at TE Wire and Cable and CCPI Europe Limited, I welcome everyone to our first ever product webinar. Our webinar will start and last until approximately 2:45 p.m. today. We will be recording this live presentation, so should you have colleagues who are interested but unable to attend, we will be posting the recording to both the TE Wire and Cable and CCPI Europe Limited websites. An email will also go out to all registrants, with the YouTube link for future watching. To get us started, we will do two brief polls that I would like to begin with, just to learn a little bit about everyone's industry and applications. So I will initiate the first poll. So the first poll question is, which industries are applicable to your organization? And okay, I'm going to close the first poll. I'm going to initiate the second one. So which processes are applicable to your organization? You should be able to select more than one option. Okay, I will close the last poll. We'll get into the presentation. Okay, so today's webinar is on the new low drift base mineral insulated thermocouple cable, or what we've been terming our low drift product. I invite everyone to download our low drift product flyer, which is available in the flyers section of your GoToWebinar control panel. As we proceed through the presentation, you are welcome to ask questions about the product using the GoToWebinar questions feature, also located in the control panel, and we will answer as many questions as time allows at the end of the presentation. Just to give a brief background of our companies, TE Wire, together with our sister company CCPI Europe Limited, have partnered to develop, promote, and distribute the low drift product. Both are members of the Marmin Group, which is a Berkshire Hathaway company. Berkshire's annual revenue totals approximately $185 billion. The Marmin Group consists of 175 different companies totaling $8 billion in annual revenue, with over 19,000 employees amongst the group. It has over 300 manufacturing distribution centers worldwide. Within the Marmin Group, TE Wire and CCPI are grouped amongst 13 additional wire and cable companies that make up the engineered wiring and cable sector. TE Wire, who has licensed the patented low drift mineral insulated technology from Cambridge Enterprises, is a specialized manufacturer of thermocouple wire and cable. It was founded in 1941 with its headquarters in Saddlebrook, New Jersey. We provide both stock and custom constructions with over 14,000 varying combinations of wire and cable. CCPI Limited manufactures thermocouples for industrial temperature sensors. It was founded in 1984 and has its principal headquarters in Sheffield in the United Kingdom. CCPI is most known for its high quality, high temperature industrial temperature sensors. Both are also companies that are ISO 9000 2015 certified and administer ISO 17025 accredited temperature laboratories. So without further ado, I would like to introduce our presenter today, Trevor Ford, the Technical Director of CCPI Limited.
Thanks, Joe, and hello everybody. As indicated there, my name is Trevor Ford, and I'll be giving the presentation today on the new low drift mineral insulated metal sheath, or MIMS, thermocouple cable. Before I go into the presentation itself, I just thought I'd give you a little bit of a rationale behind this particular presentation. This is the first of a series of planned presentations about this new low drift technology. And this particular one, as I said, is the first one, and it's going to give you the idea behind the development of this new low drift cable, why it was developed, why there was a need for it to be developed, and the history behind its actual development. So, regarding the presentation itself, I'll give you a quick overview of the presentation itself and what we're going to be talking about. Initially, we're going to be asking 3 questions and hopefully answering those questions. First of all, the first question will be, do thermocouples drift? Then we'll ask the question, what are the current options regarding low drift thermocouples? And the third and final question will be asked, why do we need a lower drift base metal thermocouple? Then we'll move on and talk about the history of the development of this new low drift technology in the form of a mineral insulated metal sheath base metal thermocouple cable, which is the subject of this presentation. In doing so, we'll have a summary of the investigation work carried out by the organisation that developed this technology, the University of Cambridge in the United Kingdom, and how their research into the causes of drift in base metal thermocouple technology led directly to the development of this new low drift technology. And finally, we'll wrap up with looking at a review of the comparative test data from some of the work done both in the CCPI and Cambridge laboratories, where we will see comparison data showing the performance of this new low drift cable in comparison directly with the conventional MI cables we use today in industry. Before we do that, though, I thought we'd just a quick reminder of what MIMS thermocouple cable is. It's where the thermocouple conductors themselves are insulated and separated from each other and the outer metal sheathing by a mineral insulant such as magnesium oxide. And the slide you're currently looking at shows the finished product, which you're probably more familiar with looking at. So into the presentation itself, and the first question, do thermocouples drift? Well, a very simple answer to that question is yes. All thermocouples suffer from the effect of a changing EMF output with time at temperature, usually a reduction in the output, particularly in the high temperature region, and this effect is known as drift. Probably a better question to ask would be, what is drift level dependent on? There are a number of factors: the thermocouple type, the environmental conditions, the temperature range of operation, and the temperatures the actually thermocouples see, just to mention a few. There are many reasons and many types of thermocouples and thermocouple designs. Some will show higher or differing levels of drift than others. But basically, most of the drift is dependent on both the thermocouple design and the environmental conditions the thermocouples actually see. As we mentioned, there are many reasons why thermocouples drift. We've mentioned a few above. But really, the detail of that is for a different presentation. The point that needs to be absorbed here is there is an issue when it comes to using thermocouples for long-term high temperature measurements. So, what are the current options regarding low drift thermocouples? Well, currently, the range of thermocouples known as the noble metal range, or the platinum rhodium based thermocouples, the types R, S and B, would always be the choice for high temperature industrial applications. This is because these thermocouples show the lowest drift characteristics of all the common standard thermocouple types we use, mainly because of the materials they're manufactured from. However, for the same reason, both for cost and mechanical limitations, these thermocouples are not always an option for industry. The cost is a fairly obvious one: the materials they're made from, the platinum rhodium group, which can be very expensive, and also the mechanical limitations. The protection mechanisms needed for these thermocouples are usually ceramic-based sheaths, which are obviously very inflexible and also quite limited in diameters. The most practical option regarding temperature sensors is the MIMS base metal thermocouple design. This MIMS design gives practical protection for the thermocouple wires for the environments they're used in. In effect, the powder and the outer metal sheathing protect the thermoconductors themselves from the environmental attack and contamination. So, for both practical and economic reasons, the Type K and Type N MIMS thermocouples are and will remain the industrial temperature of choice in this high temperature region. However, both the Type K and Type N thermocouple, particularly when we're talking about temperatures above 1000 degrees C or 1800 Fahrenheit, can also see very high levels of drift. So, why do we need a lower drift base metal thermocouple? The most widely used thermocouple types in industry, we've already mentioned, are the Type K and Type N thermocouple. The best overall option from a practical viewpoint is the MIMS design. But there is a growing demand from industry for better measurements in this higher temperature region, a more reliable measurement capability. These thermocouple designs, the Type K and Type N, have not been improved. We're using the same designs, have not been improved since the development of the Type N thermocouple itself some 50 years ago. Hence, there is a need, with this demand from industry, for a base metal thermocouple with a better performance, particularly in the higher temperature range. We've talked a lot about drift. I'd like to actually show you some typical effects of drift from some data collected by tests conducted at the Cambridge laboratories. This test was actually conducted on some conventional Type N MIMS thermocouples. They happen to be 3 mm diameter Inconel sheath constructions. And the chart we're looking at here shows us the peak performance during some cycling operations. In effect, the test thermocouples were cycled between 300 and 1200 degrees C over a 4-hour cycle period. And this cycling was repeated for some 350 hours during the test. The chart we're looking at, as I say, shows us the top 10 degrees C of these peaks. So the first line you see on the chart is the measured temperature of the peak of the actual cycles by the Type S control thermocouple of the environment, really just to indicate that the environment was seeing a steady peak temperature of 1200 degrees C plus or minus half a degree C throughout the full duration of the cycling period of the test. The first set of data we're looking at here are the blue peaks, which are the results from the conventional Type N MIMS thermocouple. Initially, the results are very close to 1200 degrees C, and for the first 2 or 3 cycles, it repeats the original value very closely. But very gradually, but consistently, you see a reduction in the peak temperature measurement indicated by this thermocouple. This is a classic example of drift, a lowering of the measured temperature of the EMF output. We know the thermocouple is still seeing the peak temperature. The Type S thermocouple is telling us that. However, it's indicating a significantly lower value, such that after 150 hours of cycling, it's seen some 2 or 3 degrees C lower, while the 300 hours of cycling is 5 or 6 degrees C lower. A classic example of drift in operation. So what I'd like to do now is introduce this new low drift thermocouple option, or thermocouple cable, that is the focus of this presentation. We've already talked about why Type K and Type N base metal thermocouples are the most widely used temperature sensor in industry, particularly in the temperature region above 800 degrees C or 1470 Fahrenheit. We've already mentioned that the MIMS construction is the best regarding its practical design, because it shows less drift than other forms. However, it also can show significantly high levels of drift above 1000 degrees C, above 1800 Fahrenheit temperature range. These are the exact reasons why researchers at the University of Cambridge, working under Dr. Michele Schiavini, have spent the last 10 years researching and developing a new low drift base metal thermocouple option. What I'd like to do now is give you a little bit of a history behind the development. And as I've already mentioned, it's been worked on now some 10 years by researchers at the University of Cambridge. They started the project looking at temperature measurement using contact sensors, i.e. thermocouples. The work focused on studying the drift characteristics of these base metal thermocouples and studying the reasons why these thermocouples actually drift in use. There was actually some very innovative testing developed by the researchers at Cambridge, to such an extent they were able to determine and categorize the drift component of the individual conductors or individual thermocouple legs of a thermocouple combination under various thermal conditions. Directly from this research, this new form of low drift MIMS, mineral insulated metal sheath thermocouple cable, has been developed directly from the research conducted in the Cambridge laboratories. So I'd like to give you an overall summary of that development. Initially, the work, as already mentioned, started looking at all thermocouple types, particularly Type K. Researchers worked on both bare wire and MIMS constructions. However, this presentation really going to focus on the drift developments and work found on the MIMS designs. What the researchers found at Cambridge on the MIMS constructions was that the main cause of drift was due to contamination coming from the outer sheathing of the construction itself. This is quite an irony, really. The design of the thermocouple with the powder and the outer metal sheathing was actually fulfilling its job of protecting the thermocouple wires from the environments and contamination from the environments in which they were located. However, now it was that the actual metal sheathing became the main source of contamination, and therefore the main source of drift. It would be difficult to change the outer sheathings because these have been designed and were fulfilling their role of design in industrial applications. But the researchers at Cambridge put forward the concept of introducing a barrier that would sit between the outer metal sheathing, and the actual thermocouple conductors themselves. And this would stop the contamination or reduce the contamination, and in turn stop or reduce the drift. When you look at the screen at the moment, you can see a schematic. On the left-hand side shows us the designs or schematic for the conventional MIs. On the right-hand side shows the concept put forward by the researchers at Cambridge. That was to have an inner wall, a second or dual or double wall design, where this dual wall or the inner wall material was made from a suitable material that would stop or reduce migration of materials from the outer wall to the conductors. What I'd like to do now is talk about, show you a set of graphics or animation that shows the concept of what the researchers found, is that under conventional conditions in high temperature, contamination was caused on the conductors from migration from the outer sheathing itself. This caused a change in the metallurgy, which caused a change in EMF output, which was the source of the drift. With this new low drift design put forward by Cambridge University researchers, this inner wall would stop or reduce this drift, and in turn stop or reduce the metallurgical contamination of the conductors, and therefore stop or change the drift. So, what I'd like to do now is show you a series of test data conducted on this new low drift cable in comparison with the conventional cables that are used in industry today. This first test was conducted at the CCPI Europe laboratories, and it was actually conducted on 3mm diameter Inconel sheathed Type K conventional MIs against the new low drift dual wall counterpart. The actual temperature conditions of the test were actually cycling conditions, and one cycle is shown on the slide. It starts at 400 degrees C, goes to 650, 850, 1050 and 1250 degrees C, holding at each temperature for 1 hour, and then cooling down to 400 degrees C. This being one cycle, this taking some 390 minutes per cycle. The actual thermocouples are subject to 91 of these cycles, or 24.4 days of continuous high temperature thermal cycling. The results we're going to look at are going to show us in chart form the change in EMF output in degrees C over those 91 cycles for the respective test thermocouples. So the chart you're looking at down the y-axis is the change in EMF output over the 91 cycles in degrees C, across the x-axis at the temperature points of calibration during the test. So first of all, let's look at the data from the conventional thermocouples. Two units were tested. First one in blue shows us the change over the 91 cycles was between 12 and 11 degrees C. The second one in red shows us it was slightly larger, between 15 and 17 degrees C over the 91 cycles. Now in comparison, under the exact same conditions, let's have a look at the performance of the new low drift design. Again, two thermocouples were tested. Both thermocouples over the complete temperature range of testing over the 91 cycles showed less than 3 degrees C movement. As predicted by the researchers at Cambridge, somewhere between a 73 and an 83% reduction in drift was observed when the new low drift thermocouple designs were compared against the conventional designs being used in industry today. This next sequence of testing was conducted at extremely high temperature of 1320 degrees C, above 2400 Fahrenheit. A temperature would not normally recommend Type K or Type N thermocouples to be used at. The actual test conducted was for some 52 hours or 2 days of operation, and the thermocouples that were tested were the same as the previous set of data, i.e. 3mm diameter Type Inconel sheath conventional against their 1/8 diameter dual wall low drift counterpart. Results we're going to look at, again in chart form, are going to show us the correction value or changes in correction value in degrees C at the test temperature of 1320 for the respective test thermocouples. So in this instance, the chart showing you the change or change in correction in degrees C down your y-axis, and the time in temperature in hours, the time in hours across your x-axis. So first of all, let's look at the performance of the conventional thermocouple. As we would have expected, a continuous drift was observed, an increase in the correction value, a lowering of the EMF output value, starting at some 3.5 degrees, moving to some nominal 15 degrees, showing a nominal 12 degrees C shift over the 52 hours of operation. Actually quite a good performance for a 3mm diameter Type K thermocouple. Now let's look at the performance of the new low drift design under the same conditions. Well, you can observe a significant difference. Again, starting off at some 3.5 degrees, but finishing at less than 5.5 degrees C correction value, less than 2 degrees C nominal movement, or, as predicted by the team of researchers at Cambridge, an 83% reduction in drift characteristics was observed. Really, from this data, and from significantly large quantities of data from tests carried out at Cambridge and CCPI, the researchers at Cambridge were able to establish and predict that the drift levels of this new design were reduced between 80 and 90% when compared to conventional designs in this high temperature region. What I'd like to do now is just recap or revisit the first set of data we looked at the beginning of the presentation to illustrate the characteristics of typical drift. So if you remember the chart where the blue peaks shows the gradual but continuous drift of a conventional MI thermocouple, under the exact same conditions I can add the data from the new low drift design. This is shown in green. The actual value starts off with a correction value of about 3.5 to 4 degrees C. But the beauty about this is that that value is maintained throughout the full duration of the test to a level of probably better than plus or minus 1 degree C, and really shows the contrast between the new low drift design and that of the conventional design that shows the continuous, gradual but continuous drift characteristics, whereas the new low drift design shows this repeatability of measurement. So we've looked at data from CCPI labs and the CCPI Europe laboratories. Has it been independently verified? Well, there have been some European funded programs called the EMPRESS program. The EMPRESS 1 program was a 3-year program that finished earlier on this year. The EMPRESS 2 program is a program that actually started and will run for 3 years, started earlier on this year. Both these programs have seen this new low drift design tested by various European national measurement institutes. In addition to this, there has been independent testing in real-life industrial applications. All of the data from these tests have confirmed the results as found by CCPI and Cambridge, that this new low drift design, when compared to the conventional designs we're using today in this high temperature region, show a significant reduction in drift characteristics. So, the advantages of this new low drift cable. We've obviously been talking about the reduction in drift, i.e. greater than 80% in this high temperature region, which is obviously the main advantage. These results have been independently confirmed. But another major advantage of this new low drift design is that the thermocouples are still Type K or Type N thermocouples and perform exactly like the Type K or Type N thermocouple when it comes to the EMF output values. As far as the operators or users are concerned, no changes in instrumentation, wiring, or the operational procedures are actually required. The only thing the operators, the users, will see is simply a base metal thermocouple with a significantly superior performance, a better measurement capability, a lower drift operation. Overall, this is why we can say with confidence this new low drift technology is the greatest advance in base metal thermocouple technology since the development of the Type N thermocouple in the mid-1960s for over 50 years. So that really brings the presentation part to a conclusion. I'd just like to summarize what we've been talking about. First of all, we've looked at why thermocouples drift and given a brief overview of that. We've discussed why there's a need for a low drift thermocouple. In the industry is demanding higher temperature operations and better measurement capabilities. We've talked about the history and how Cambridge University researchers developed this new low drift cable directly from the research conducted in the labs. And we've looked at some comparative test data that shows the superior performance of this new low drift cable in operational conditions. At this stage, I'd just like to thank everybody for listening, thank Joe and his team for setting up this webinar, and hand you back over to Joe.
Thank you, Trevor, for a very informative session. To those watching, If you're interested in additional information or possibly even a quote, I welcome you to contact our sales teams. If you reside in North America, out of the Saddlebrook office in New Jersey, we have Patrick Durkin, who's our VP of Sales. His contact information is listed on screen. If you reside in Europe, Julie Dickinson, who's the sales manager of CCPI Europe Limited in the UK, would be the contact person for additional information or quotes, and her contact information is also listed as well. For convenience, we'll be sending this information out via email in our follow-up email. So we'll be moving on to the question portion of our low drift webinar momentarily as we wait for some additional questions to come in and be compiled by my colleague. I will briefly just announce some upcoming events. This year, TE Wire will be at the Furnaces North America Trade Show. That will be taking place in Indianapolis, Indiana, and that's from October 8th to the 10th. We'll be at booth 127. I welcome you to join us. We'll also be participating at this year's CAMEX exposition. That will be in Dallas, Texas, and that is from the 16th to the 18th. We'll be at booth CC28. And just lastly, a little shameless plug before we get into the questions. We do have our seasonal summer short length sale, which features discounts on all our stock short length material, essentially spools under 1,000 feet. The last day to purchase is July 31st. Items are on a first come, first served basis, and I definitely encourage everyone to partake in that. So it does look like we have some questions here, Trevor. So why don't we just get right into it. The first two, it looks like, are really more for me. Where can I download the white paper? So the white paper is available on our website. If you haven't already had a chance to read it, for your convenience, I'll try to send out a link for download to all registrants and our follow-up email. Can I receive a sample of the product? So the answer to that is yes, samples are available. You may contact our sales team to submit a sample order. We do request feedback upon samples having been used, as well as the sample to be returned for study. Again, the contact information for our sales department will be available in our follow-up email, should you not have been able to write it down previously. Trevor, I'm going to ask for your help on this next one. Impact junction response time for the low drift mineral insulated cable.
Right, it's quite a good question, actually. The initial or the first generation of these thermocouples were designed and had a significantly thicker wall than a conventional MI thermocouple, and accordingly it did have an impact on response time, obviously being slower. However, which is also going to be the subject of a second or third webinar, we have actually started developing the second generation of these new low drift thermocouples, and these have significantly thinner walls. In fact, far more like the conventional MI cable, and their response time is virtually identical, if not identical, to the conventional MI cables.
Okay, so the next question, available junction types?
I'm not quite sure if they're referring to either cold or hot junctions, but basically the answer is the same for both. It is, as far as the user is concerned, an MI thermocouple and will look and seem like a standard MI thermocouple, just one that's had a significantly superior low drift performance, and therefore both hot junction variations and cold junction termination variations are available as per the standard units.
Any sheath diameter restrictions?
Well, at the moment we've only managed to manufacture the unit down to 1.5 or 1/6 of an inch diameter. So at the moment, yes, there is a restriction on those as indicated. However, in the future we do plan to move on and manufacture smaller diameters, and again that will be the subject of another presentation.
To what degree is sensor rigidity affected?
As I indicated above, for the initial generation or first generation, with having the thicker wall, they're obviously significantly more difficult to bend and stiffer units. However, the second generation perform exactly like standard MIs as far as the rigidity or flexibility is concerned.
Compared to traditional mineral insulated cables, any additional care required or usage restrictions?
None whatsoever. In fact, the thermocouple itself will perform in respect of durability exactly like a standard MI thermocouple. I mean, the only restrictions will be is that this thermocouple will last a lot longer than probably most specifications will allow the user to work them over.
Is it safe to bend?
Very much so. It is, in effect, to all intents and purposes, a standard MI thermocouple cable as far as the bending is concerned. The first generation will be a little bit more stiffer to bend as indicated, but other than that, no limitations.
Okay. So we do have a few additional questions here coming in. I'm just going to recite these. Trevor, one individual is asking if the bend radius is the same as a single wall mineral insulated cable.
The performance of them, and as far as the work we've done to date, shows that when we're talking about the second generation units, the answer to that question is yes. The first generation will be more limited, but they're obviously can be used for where the application needs less flexibility.
Okay, just going to skim here. So one person has asked if this is going to be available online. Yes, we did record this. So if you missed a part or you want to go back, we will have that on our website. Question here on junctions, Trevor. Exposed junctions, grounded junctions, or ungrounded junctions. I guess they want to know if that's available.
They all will be available. Obviously, exposed junctions is not, depending on the environment, it can be restricted. Obviously, if you expose the thermocouple wires themselves, the protection mechanism of the dual wall low drift design is actually lost at that point. But they will be available as all conventional MI thermocouple junctions are.
Okay, we have a question here on wall sheath. Is it a seamless wall sheath or welded wall sheath?
It's a seamless wall sheath as per standard MI type constructions.
Let's see, one more here. How does the second wall of the enhanced MIMS affect junction response times?
Well, that's a little bit like the question answered earlier. The first generation will, with a thicker wall, will slow the response down. The second generation will perform as per standard units.
That's pretty much it. I think we're going to have to conclude here. This concludes our low drift webinar. Once again, thank you, Trevor. And I'd like to thank all who have attended. This will be the first of a series of webinars on this technology. We hope you liked it. Please let us know if you did. We welcome all comments and are very eager to see you all in future webinars. Thank you and have a wonderful day.